derive the relation between Cp, that is molar specific heat capacity at constant pressure, and Cv. This is also known as Meyers equation. Now let us consider a piston and a barrel assembly. This is a barrel or cylinder inside which we have the piston like this. So this is cylinder or barrel, and this is piston, and this piston should be weightless, frictionless. Now its pressure is P, volume is V, and you have got the temperature T. The area of cross section of the piston, you can call it area of the piston as A. So A is equal to area of the piston. And inside which we have got the ideal gas. So ideal gas inside the cylinder. Ideal gas is present inside the cylinder. And we have got the weightless, frictionless, piston that adopts to and fro motion. That causes compression and expansion. We know during compression pressure increases, volume decreases. During expansion, volume increases, pressure decreases. And we bring these changes at constant temperature. It means isothermal. Isothermal process. And the dQ, the small quantity of heat, is transferred. Small quantity of heat is transferred from system to surrounding or surrounding to system. and that is responsible for the small increase in the temperature also. So in that case, initially it was T, now T plus dt. Because of the increase in pressure from P to P plus dP. And this dQ is given by the small change in heat transfer. The heat transfer is nothing but change in internal energy, that is given by, we already know Q is equal to M S delta T. So based on the dQ, means here I have considered 1 kg of mass, so I can put 1 into CV at constant volume. So what is CV? Molar specific heat capacity at constant volume. Cp means at constant pressure into the small increase in temperature, dT, or you can call it temperature element also. And dQ can be called heat transfer element. Small change or instantaneous change. Now, dQ is equal to du, that is change in internal energy, into 1 into Cv into dt. Now the piston moves up to cause an expansion. Say, let us call it a dx distance like this. So the piston moves upward to dx distance, small distance. Small distance. Okay. So initially I kept a cylinder here, we have got the piston, and I put some weight also here, some weight. And now it has caused some, what, that is increase in pressure. So P plus dP, and volume remains as such, but the temperature is T plus dt in this case. And at that time, the quantity of heat transferred is dQ. This is the quantity of heat transfer. Now I am removing the weight. Okay, the next case is I am just removing the weight. So this is the first one, first diagram. This is the second diagram where I have placed the weight. and thereby it exerts a pressure, additional pressure. Now I have removed the weight, and that is subjected to some kind of expansion. So initially it was here, now the piston has moved up to how much distance? Dx distance. So the piston has moved up. And what about the pressure? Pressure was maintained constant, but there is a change of volume, or you will follow here because of the weight, the volume is kept constant. Do you understand? But in this case, what am I changing? I am changing the volume. So since I removed the weight, so there is an expansion, and therefore V plus small delta V. And temperature also changes from T plus dt. Okay. So here the heat is given absorbed at the transfer as dq dash. Let me put dq dash. So in this case, I am calculating the dq dash as according to first law of thermodynamics, du plus dw. Now this dq dash is also given as, because it is done at constant pressure. If it is done at constant pressure, then it is Cp dt, is it not? So Cp dt. Got it? But in this case, it was done at constant volume. So here, how to write down? dq is equal to Cv dt, or you will follow? Remember here. So in this case, I put Cv dt because the volume was constant. Okay. So here at constant volume. That is why I used this term as Cv, that is molar specific heat capacity at constant volume. Here it is at constant pressure. Here at constant volume. So for constant pressure, I have to use this term Cp, that is molar specific heat capacity at constant pressure. Okay. Now we have another equation, Cq dash is equal to Cp dt. So here I can substitute this Cp dt is equal to du plus dw, is it not? And du is nothing but we have got already in this equation. So let me number this equation so that you will find it comfortable. So this is the first equation, this is second equation, this is third equation. Now you can substitute the third 3 and also 1 in this equation. So instead of du, I can make use of this equation, is it not? Therefore Cp dt is equal to, instead of du, I can take Cv dt, correct, plus dw. Okay, is it clear? Now work done. Let us talk about this. So this is the fourth equation. This is a very important equation. Now what is work done? Work done is represented by W is equal to force into displacement. Is it not? Force into displacement. And infinitesimally small work done means force into infinitesimally small displacement ds. So since we have introduced x here, I can replace this by dx. So f into dx. Got it? So what is my work here? dw is equal to force into displacement. Got it? Next. Now we know pressure is equal to force by area. So force is equal to pressure into area. Okay? So therefore we already know dw is equal to, what is the equation? F into dx. So I can replace this f here. Therefore dw is equal to p into a dx. A dx is nothing but the small change in volume, is it not? Some area of cross section, and it has moved to a certain distance, means this is area and this is dx. So area into the length factor means volume, is it not? So that results change in volume, and that's why I put, that is here I can take this as change in volume. Got it? Therefore dw can be replaced by p into dv. Okay, p is equal to dw is equal to p into dv. Okay, now we have got the equation. What is that equation? Cp dt is equal to cv dt, is it not? cv dt, and then we have this dw, is it not? So we have this dw, we can replace this. Therefore instead of dw we can put pdv. So cp dt is equal to cv dt plus pdv. Are you will follow? And according to ideal gas equation, PV is equal to RT, where R is gas constant, T temperature, and now we can differentiate this. So PdV is equal to R into dt, is it not? So I can replace this PdV by R dt. Therefore Cp dt is equal to Cv dt plus R dt. Now I can divide the entire equation by dt. So multiply this by 1 by dt. Therefore Cp is equal to Cv plus R. That is, you can bring the Cv this side. So Cp minus Cv is equal to R. So this is called Meyers equation. Okay.